Alright, so this is going to be a quick overview of the Fusor. I don't know much longer I'm going to have this thing in operation or actually even assembled, because I'm going to be moving on to some other projects that require the pumping system. So this is going to be a quick walkthrough of exactly how it is set up and arranged. First thing I'll do is talk about the Fusor itself. Underneath all this lead shielding in the lead box is the Fusor. And I'll back out here for a second and I'll show you a picture of exactly what the Fusor looks like without all this lead shielding. Okay, so as you probably noticed with that picture, there's a few cooling lines coming off the Fusor. And they do go down into this bucket of coolant, and there's the pump running right there. And as you can see, it is pumping. If I don't pinch the hose, it's pumping out the water for coolant. Same pump type arrangement is set up for the diffusion pump over here. To maintain operation for that system. And what you see running here is the roughing pump for the diffusion pump. Okay, so the heart of the Fusor is this power supply that I built. It is a custom-made 4-flyback arrangement, which is run in series. Each flyback has its own voltage multiplier circuit. So each individual flyback is capable of putting out about 20 to 25 kilovolts, and so this makes about 100 kilovolts maximum if I ran this thing full tilt. I really don't run this thing past 80,000 volts. There hasn't been a need to, because the Neutron output has been sufficient. The power supply is kept under mineral oil, and here is a picture of the power supply outside of the containment system prior to getting it all put together. All right, the positive output of the power supply is fed into the feed-through that is shown right here at the bottom of the Fusor. Feed-through is submerged in mineral oil itself, which gives a standoff potential of between 90 and 120 kilovolts. I haven't really gone above 85 to 90 kilovolts, but there hasn't been any indication of electrical leakage. Okay, so on this side is the driver circuit for the power supply. It's a simple ZVS driver. This is about a $35, $40 ZVS driver from Amazon. You can also get them on eBay. It's more than enough power to drive all 4 flybacks in parallel, which is how it's currently set up. To drive power to ZVS driver is a large rewound microwave oven transformer. And you can see the number 10 windings here on the secondary of the submerged microwave oven transformer. It is submerged in mineral oil. Rectifying the power out of the microwave oven transformer is a 50 amp full wave bridge rectifier going into a filter capacitor. I do have some crude monitoring set up for voltage output, and another setup for current, as you can see. I do have a fan cooling the ZVS driver in addition to the fan that's already on top of it. Okay, on this end is the analog monitoring metering system. So what I've got here is a vacuum gauge. I do not have the secondary diffusion pump kicked in right now, and so it's at about 10 millitorr of vacuum based on the roughing pump. When I kick the diffusion pump in, it takes about 10 to 15 minutes, and this thing drops to sub-millitorr levels. Directly behind here is a meter for measuring Fusor current. Operation for this to get into the 2 to 3 million neutrons per second output is about 2 to 2.5 milliamps at about 65 to 70 kilovolts. Okay, shown here is the valving system for the deuterium input. Deuterium from a 100 milliliter syringe is fed in here. This is a SS-SS4 needle valve. I'm sorry, I got this backwards. So this is a medium flow valve. This is an SS-SS4 valve. And here's just a gate valve for turning off the entire gas flow system. Gas from the syringe is fed directly into this point here through a small 2 millimeter silicone tube. Okay, so Fusor wall chamber temperature is monitored by a thermocouple attached on the other side of this yellow line. It goes down here to this Type K reader. Fusor wall temperature is currently at 76.4 degrees Fahrenheit. Optimal range for operation is probably between 40 degrees Fahrenheit and no more than 85 degrees. Anything above 85, you'll notice a change in neutron output. It starts to degrade a little bit. So I try to keep it usually at around 60 or below. There's a very crude sort of DC kilovolt meter to give me an idea of where I'm at in the voltage levels. Okay, so about 22 feet away from the Fusor is this variac, which is what I use to control Fusor input and increasing my neutron output. So you can see, I'll back out here a little bit, the Fusor is all the way over here, and I do have this Ludlam Model 3 that I use for radiation monitoring, and from this point all the way back here I do not get any detectable radiation signature from the Fusor. Just for comparative analysis, the average granite countertop from a kitchen puts out more radiation than I'm detecting from the Fusor at this point. Just as a extra precaution, I have placed an old X-ray vest here next to me, so I don't know, just in case some sort of accident should happen, but I highly doubt that would be the case. Okay, so here we are back at the Fusor. Directly underneath this lead shield is the moderator for the neutron detector. The neutron detector is a CHM11 boron tube. This size of moderator has been calibrated with a BTI Industries bubble neutron dosimeter, and it registers an output with a Ludlam 2221 rate meter. Okay, one last thing just to discuss about all this lead shielding. The lead shielding is mainly to control any X-ray output. The Fusor chamber is made out of aluminum, so it's fairly transparent to X-rays. So it's kind of necessary to have additional shielding, because even with the inverse square law, with absolutely no shielding, and when you're running over 50 or 60 kilovolts, it puts out a little bit of X-rays, at least to the point where you shouldn't be around them too long. A dental X-ray or an X-ray at the hospital puts out significantly more, but minimizing any X-ray signature is of utmost importance. So I do have the shielding, and there is one more X-ray apron right here just to address any potential leakage coming off of the ceramic feed-through. Okay, so regarding operational parameters, in order to get between 1.5 and 2.5 or even 3 million neutrons per second, what you basically need is between 2 and 3 milliamps of current draw. Okay, and your deuterium pressure should be between just about 35 to 37 millitorr of deuterium pressure. If you go much lower, then the voltage going into the system ramps up a little bit too much, up into the 80 to 90 kilovolt range, which kind of exceeds my routing hardware. So I try to keep it no lower than 37 millitorr. And again, that's more than enough to give the neutron output needed for activation experiments. One other important thing to note specific to the power supply and just the whole operation of the fusor, when you are operating the fusor and you first turn it on, it's not like you can immediately just turn the knob up to the proper settings and immediately get, 1.5 million or 2 million neutrons per second. It's a slow ramp up. You're going to probably start at about 25 or 30,000 neutrons per second. Then you walk it up to 100 and slowly walk it up to 500,000. And probably in about 15 to 20 minutes, maybe less, you can get yourself at about 1.5 million neutrons per second or more. So it's not too difficult to get what you need, but you do not want to move fast. If you move fast, you're just going to draw too much current. You could potentially damage the power supply, or possibly even damage the ceramic feed through. Okay, so a quick note on these coolant tanks. All right, specific to the diffusion pump, okay, it heats up this amount of coolant pretty quick. So you want to keep your coolant in the diffusion pump cool, hence the name coolant. It's important to fill this up with ice so you can keep the temperature probably around 50, 40 degrees. You can have a little bit more than that, but I would always insist upon keeping enough ice in this diffusion pump bucket to keep the temperature low. Now, the coolant bucket for the fusor itself, you almost don't need to have ice in here. Okay, it is very efficient at removing the heat from the fusor. But if you want to do a long sustained run, half hour, 40 minutes, where you're doing some heavy duty activation, you're going to want to put ice in there and do your best to keep the temperature at 60 or below degrees. It's just more efficient, and actually the cooler you run the fusor chamber, the higher the neutron output. You will not have any degradation of neutron output as long as you just keep that chamber nice and cool. So for longer runs, you do want to put ice in there. Okay, here's a quick little overview of the PIM cell. Converting heavy water, deuterium oxide, into deuterium gas. As you can see, the deuterium gas outlet is fed through a small 2 millimeter silicone tube into the plastic syringe itself. It's only powered by a couple of D batteries. While under current draw, it's only pulling about 2.75 volts, which seems to be optimal for this type of PIM cell made by the Horizon company. Okay, so the diffusion pump has been turned on, and I just want to highlight one interesting little thing that happens when you turn the diffusion pump on. So if you recall, before I turned the diffusion pump on, this thing was at about 10 microns or 10 millitorr, and now it is about 27 millitorr. That is perfectly normal. So what happens when you turn on the diffusion pump, it heats up the diffusion pump oil and causes whatever moisture is in the system to actually start backflowing into the fusor just a tad, and it causes a pressure burp or a pressure increase in the entire system. Now, this is only temporary until the diffusion pump hits its optimal heating temperature, and once it kicks in and actually starts working, it's going to drop down to 0. And if I had a different type of meter to register submicron levels, you'll see it would probably drop down to probably about 1/2 a micron or 1/2 a millitorr, or even less than that. So, but such low micron levels or millitorr levels, vacuum levels, whatever you want to call it, aren't necessary for a fusor, because fusors generally operate between 7 to sometimes even as high as 30 millitorr, depending on the size of your fusor. And again, sometimes even 40 or 50 millitorr, depending on the size of your fusor. This fusor I would classify as a middle of the ground, mid-sized fusor. Not the smallest, but definitely not the biggest. and its optimal temperature range, pressure range for deuterium is about 35 to 37 millitorr. Okay, and lastly, before I start getting into the operation of the Fusor, meaning actually turning this thing on, it's important to note that there's a little bit of a differential pumping action that you have to employ when running the Fusor. And even though you get this thing set up to operate at 37 millitorr of deuterium pressure, okay, if you don't have the throttling of the diffusion pump set up properly, it's just not going to give you the neutron output that you need. So in other words, you need this thing to pump enough deuterium into the system and have it evacuated by the diffusion pump at the same time, meaning you need the flow to not be like really stagnant or very slow. You need to have the deuterium flow set just about right. You don't want it almost down to zero. You just want it somewhere in the middle. And unfortunately, it's not something that can be really described over a video like this. You'll have to actually operate it. But you just don't want it to go at a snail's pace. So I have found on the throttle valve down here for the diffusion pump, what you want to do is close this thing off completely once the diffusion pump has hit its proper vacuum, and then turn the knob counterclockwise just about 2.5 to 3 times. That is just about the sweet spot for getting the differential pumping completely set up for this Fusor, at least to make it operate properly. Anything less than that, if you only open it up like about, 1 turn or 1.5 turns, it's just not gonna do it. All right, so what I got here is a fast neutron detector. This one's kind of an old one, but it still seems to be working okay. This very well could be the last time it's going to operate, but anyway, this will register fast neutron output in the form of bubbles in the fluid matrix here in the little test tube end. So what I'm going to do is I'm going to put this back inside its protective tubing after I set the neutron detector for detection, and I'm going to go ahead and set it on top of the Fusor to register neutron dosimetry. Okay, you can see I placed it right up here against the Fusor. This is actually a little bit closer than what the neutron detector would be. So this is at about 11 centimeters or so from the core of the Fusor itself. Okay, so as you can see, I've got the syringe of deuterium gas attached to the gas inlet system. It's pinched off with a hemostat or forceps, whatever you want to call it. The diffusion pump has kicked in. I'm down to below submicron levels, or into the submicron level. That sounds funny, but you get my point. And so it's really important on these systems. This line here is just filled up with junk air, so you want to purge the system. So that is, keep the hemostat clipping off the deuterium flow. Then what you want to do, you'll see the meter jump here, you want to open up all these valves, okay? And you want to get them completely opened up until the entire line is purged. Okay, until it gets down to 0 again. Once it's down to 0, you're good to actually start setting this thing for your 37 to 40 millitorr of deuterium flow. Okay, all right, so I'm gonna back out of here and I'm gonna get that part all set up. All right, so I actually skipped over one part that's kind of important. You wanna prime the system with fresh deuterium before you get it set up. So, you turn off your needle valves, keep your gate valve open, and remove the hemostat. You're still at 0, so what you want to do, okay, is set your valves and prime the system. So just let it shoot up to about 50 or 80 millitorr a couple of times. You can see you're not using hardly any gas, so it's not really a waste. It's just very small because they are needle valves. Okay, I usually do it twice. Okay, that's more than enough. Okay, let it go back down to 0. And now you're set. So you can go ahead and set the throttle valve on your diffusion pump to the 2.5 turns that I was telling you about. And then you can come back here to the needle valves and establish your 37 millitorr vacuum. All right, so here we are set at our 37 millitorr. We're gonna go back to the voltage control point and I'll show you how to get that operated. Okay, so ZVS drivers have to be abruptly started. You can't slowly ramp up the voltage from 0 to 12 volts. My ZVS driver has a kickstart or starting voltage of about 12 volts. All right, so you actually have to turn this up to about 12 volts. Okay, I already know that this setting right here is 12 volts from prior experience. So you need to set it up for 12 volts first, or maybe a little bit more before turning it on. Okay, the power strip is still turned off. Okay, and then from this point forward, I can go ahead and turn on the Fusor to get it going. All right, so, and that's what I'm going to do. All right, so there's the Fusor. And we should start hearing some beeps as soon as I turn this thing on. That's gonna be neutrons. Okay. Doesn't take long to start kicking up some neutrons. All right, and as I stated earlier, you have to go slow getting this thing ramped up. The neutron bubble dosimeter, I can guarantee you, is already registering some bubbles. I'm at about 50 kilovolts. Fusor chamber temperature is at 78. I'm not going to worry about that too much because I'm not doing a long run. This is just a quick run for demonstration purposes. And my milliamps is actually below 1 milliamp. So I'm going to start pushing this thing up to about 2 milliamps, and then I'm going to turn the video back on so you can see where we're at. Just for a note, we're registering right now about 2600 raw counts per minute. That's not tier of neutrons. Okay, so here we are at roughly a little over 1.2 million neutrons per second. You can see the count rate on the detector is at about 14,000 counts per minute. So with the dosimeter and the calibration, that equates to a tier output of over 1.2, 1.3 million neutrons per second output. Fusor chamber temperature is at 87.9 degrees, 88 degrees. And we kind of maxed out on this particular kilovolt meter at 50, but from prior experience, I'm at about 67 kilovolts. Let's get a little bit closer. I am at 1 milliamp, still at about 37 millitorr vacuum. The ZVS driver is at about 21 volts, and it's pulling 21 amps. Okay. Okay, so at this rate, at 22, almost 23,000 counts per minute, is roughly over 2 million neutrons per second. My chamber temperature is getting pretty high now, so at about 95, 96 degrees, that's too much. I'm at 2 milliamps. I'm at about 22 volts, 22 amps on the ZVS driver circuit. So let's go ahead and cut it down here. That's good for the demonstration, and let's go ahead and see what our bubble dosimeter shows. All right, so the whole system's been shut down. I turned off the diffusion pump. You can see the chamber temperature is starting to drop down to 83.2 degrees. Voltage is 0. Turned off the gas. Everything is 0. Power supply is 0. So let's go over here to the bubble dosimeter. And let's go ahead and open this up and see what we got. Oh, I already see some bubbles. All right. Sorry about that. Okay, so we got quite a few bubbles in the dosimeter. Each bubble is representative of about 1,000 registered counts. And there's a mathematical formula that you follow. There's a website that actually has an online calculator to tell you exactly what the tier output level is. Unfortunately, this is just a demonstration. This is not a timed count, so I can't give you exactly what the dose rate was based on the dosimeter here itself. This is just to show that I was making neutrons, and you will see the bubbles here to indicate that that is the case. Every bit of this is neutrons, fast neutrons being detected. However, as I pointed out before, the moderator and the CHM11 Ludlam 2221 detector arrangement has been calibrated, so the numbers that I was quoting earlier are fairly accurate. So, but anyway, there you go. And you can see that serial number matches up with that serial number. So there you go. All right, so that concludes this demonstration overview of the Fusor. Hopefully I covered most of the important topics. I do have additional detail in other files demonstrating how the individual systems work and how they were built and so on and so forth. But I think for the purposes of the way this arrangement is set up, it provides a pretty good representation of how the system operates, what's needed to get it going, and a little bit of info on each individual component.